Okay, hello everyone, welcome back. So let's talk about now the values for Q, or the signs of Q, which is um, the heat transferred in a system and surroundings, and W stands for the work done. Okay, so if energy is absorbed, Q is positive. So that makes sense, right? Because when things absorb energy, or the value of energy should increase, so Q is positive. Okay. If energy is released to the surroundings, then we say Q is negative, so things are getting more cold. For example, if you let some a nice batch of delicious French fries go cold, right? Eventually, they won't be as good, and they'll kind of be um, usually when we let things cool like that, they become not as delectable, right? So it's losing heat, right? So piping hot pile of French fries, it'll lose when it loses heat. We say the energy from the French fries is going to the surroundings, and its temperature, or the energy it once had, is decreasing. So it's negative. Okay. So let's talk about the signs for work. Okay. So, if work is done on surroundings by the system, that is expansion. For example, when you expand a gas to the atmosphere, and if the volume, say you have a balloon, right? So when you heat up a gas in a balloon, the balloon expands, and that's because the gas is doing work on the balloon, expanding its volume, because it can be expand. It's elastic, right? So the sign of W in this case is negative. So it's negative because we're using energy from the system and transferring it to the surroundings, and that's why the volume increases. So in this case, it's going to be negative. Okay. Now, if we compress a system, is work done on the system by the surroundings. So in this case, we're adding energy into the system by compressing the gas molecules, right? Or it doesn't have to be gas molecules, but any system. But for example, if we have a gas and we compress it, right, we're increasing the pressure by decreasing the volume. And if things are moving, if we increase the pressure, that means the velocity, gas particles will increase, right? So in this case, we say energy is entering the system, and it's giving the gas particles higher kinetic energy, or higher energy than it once had. So the sign of W in this case is positive. Okay. So, so let's summarize here. Expansion, system loses energy. Okay. Compression, system gains energy. All right. So let's kind of summarize here. So in the first scenario, first experiment, the container was kept at a constant pressure. Oh, sorry, not volume, because it wasn't the volume was fixed, right? So it wasn't allowed to be changed. So we say constant volume. In the second experiment, the volume of the gas changed, right? Because the piston was allowed to move up, right? But the container was kept at constant pressure, and that's because the piston, even though it's gaining pressure, the gas molecules are going to increase in pressure due to temperature. Due to the fact that the piston can move up, the pressure is going to remain constant because the volume is always increasing to kind of compensate for that increase in pressure. So I kind of summarized it here. The piston moved to maintain a balance between the pressure, increasing pressure by the gas in the container, and the pressure pushing down on the gas from the piston. So to kind of negate that increase, the piston moved to decrease the pressure. Okay. All right. Let's kind of test what we have just learned. So if the same quantity of heat is transferred, so if the same quantity of heat is transferred from the brick to the gas in a fixed volume piston cylinder apparatus, okay, and in a movable piston cylinder apparatus, so the two scenarios we just looked at, in which container will the fixed temperature, in which container will the temperature of the gas increase the most? So let's just write our two scenarios here. So in the constant volume, remember we said delta E equals the amount of heat transferred at constant volume. So that's our first scenario here. And then we have delta E equals Q plus work done on the by the system or on the system. So this will be at constant pressure. Remember, constant volume, no work is done by the system on the surroundings, so no heat is lost to the surroundings. Ideally, if you have an insulated container. Here is constant pressure. Remember, constant pressure though, your volume is changing, so you're actually using work to, you're actually doing work to, you're actually doing work to increase the volume, right? So you're actually losing energy to do work. Okay. All right. So in this case, heat is lost to work. At constant pressure. So this will cause the temperature of the gas to not be as high as the first scenario, and that's because we're losing energy to do work instead of heating the gas. So the temperature should be increase the most for the constant volume apparatus. So temperature of the gas will increase the least. Okay, so I kind of answered the question by stating the converse here. So in this case, this is our answer here. So no heat loss to work. Okay, so our answer here is the fixed volume apparatus. Say fixed volume piston cylinder apparatus. So that's our answer. Okay, and that has to do with how energy is being transferred between the two containers. One's at fixed volume, one's at a fixed pressure. Okay. All right. All right. So now let's talk about enthalpy. So enthalpy is actually pretty interesting concept. So enthalpy is what we define the energy or heat of a chemical reaction at constant pressure. So usually reactions are done in the open atmosphere, and so usually we have a scenario like the second one where it's delta E equals Q plus W. Okay, so experiments done, typically in the lab, they're open flask at constant pressure. So we're not usually doing them in closed containers or very pressure safe situations. So we sometimes we use what we call a bomb to do chemical reactions, because in combustion you're trying to blow things up. You're trying to blow organic compounds into lots of gases, and we need a special container to measure the heat content, and that usually carries with it some degree of danger. So we need to use special steel containers that can withstand the brunt force or brute force of a chemical release of chemical energy. Okay, so these are, say, a constant volume. Okay, so you may have heard of coffee cup calorimeters. These are the calorimeters we usually do at constant pressure. Sorry, not constant volume. These are the ones we use. Constant pressure. Constant volume is the special case where we measure the combustion of, say, a compound. So usually we work with constant pressure, and these are usually what we associate with when we say coffee cup calorimetry. So that's a common experiment that we do in lab to measure the energy content of a chemical reaction. Okay, so let's talk about that now. Instead of pushing against the piston, so instead of doing this gas example, a chemical reaction, expanding system will push against the weight of the atmosphere in an open flask. So an open flask, right, there's going to be an air around it. So essentially what's happening is the heat that's transferred from the reaction is going to heat up the gases, and it's going to push against the air or atmosphere. So we say atmosphere in this case. Atmosphere. Okay. So a system in open flask therefore has to do work to expand, and also I think this should have said and. Sorry about that. So basically, a system in open flask has to do work to expand, and in this process, it loses some energy when this happens. Okay, so not all the energy is going to be converted to heating up the sample, right? So whatever the products is, release some energy, and that will expand. Will do work to expand and push against the weight of the atmosphere. Okay. So, however, if a system in an open flask contracts, that means the atmosphere kind of pushes down on the system, so it's kind of losing energy, and so it's actually the surrounding is losing energy because there's no energy being transferred to push against the atmosphere. So in this sense, the system gains energy. Okay. So, but in either case of this process, for these processes carried under conditions of constant pressure, we can write the first law like this. So, change in energy equals the change in the internal energy plus P delta V. So this may seem a little odd, but I'm going to go into what these mean. So U is internal energy of the system. So internal energy is the energy that the system had. So that's a term you may see in thermodynamics. And especially if you're studying to become a chemical engineer, you'll definitely see that in some engineering courses. And then P, remember, we can represent work as, so work is commonly defined as, in a chemical system, pressure, we call this pressure volume work. So pressure volume work. Okay, it has units of liters like ATM. So this is a unit of force. So this is a force unit. So we could define this in terms of energy. Okay. So this is another term for energy. So basically, what we have here is that this is so this is usually an energy term. So energy. Okay. So another energy term. Okay. So for our example, if we have a chemical system here, change in energy, total equals the change in energy of the gas. Okay? Minus work plus change in energy of the surroundings. So that should be equal to 0, right? Okay. So what we could equate this equation even further by saying delta E, okay, over gas minus W, okay, equals delta E, energy over surroundings. Okay, so one thing we should make sense of is that when we say delta E, that means internal energy. So we can say delta E of gas equals delta U of the gas. And for internal energy, we know that the amount of energy a gas has is due to the amount of heat transferred, Q, plus W. And any amount of work done on the system, okay? Okay. So we can equate it to that. So that's the sum of the energy that we've seen before, right? In the previous equation we wrote a couple of pages up. All right. So the experiment shown in this first example is done at constant volume. So the first example we saw, right? It's done at constant volume. Because the piston was not allowed to move in the cylinder, right? So it was done at constant volume. The volume didn't change. So as we have seen but previously, the changes in the system and its surroundings can result from the transfer of heat under conditions of, we could say it's under conditions of constant volume. So we could actually describe these things in terms of the energy of the system. So if we're considering the first situation, right, we have a QV relationship, or sorry, we have a constant volume relationship. So we could say the change in energy of the system equals, in this case, is going to be the amount of heat plus work. But in this case, and then it's right. It's in this case, remember, we also have plus the energy of the due to pressure work. So in this case, in a constant volume situation, right? In constant volume, we have change in pressure times V. Constant volume. So the volume is not changing, right? So it's just going to be one value. Now, we know that in a constant volume relationship, no work is done. So no work is done. So we could simplify this equation to delta E of the system equals Q phi. Okay, and that just denotes it's done at constant volume. All right, so we're going to put constant volume here. And that's because this will go to 0, and then there's not going to be any work done on the system, so this also goes to 0. So it's only change of system is going to be equal to the energy transferred between the surroundings and the system. Okay? So the amount of energy that was transferred between the system and surrounding is going to be QV. Okay, and here's an example of that. So here we have a bomb calorimeter, and then in the center there, that's our reaction vessel, and then surrounding the reaction vessel is water, where we detect a change in temperature, so we can detect how much heat was evolved. So that's just like we did in those energy problems we did earlier. Okay. Now, however, now let's take and I kind of explained it here. See here, delta E of the system is internal energy plus the change plus work, which is pressure changes in pressure and volume. So when we describe work, usually we can relate it in terms of changes of pressure and volume. That's what we have been talking about. So that's why I wrote this equation. But if you look here, no work can be done on the surroundings, so the PV term goes to 0. And this is a typo, sorry about that. And a change in energy is pretty much the change in the energy of the system, so or the amount of heat released. So we denote it as QV right there. Okay, so I kind of explained it and then reiterate it like that. Okay. All right, so let's stop there and we'll talk about the second example in the next video. Okay, so I'll see everyone in the next video.